session, and Kishor will cover some basic topology for topological quantum codes. And please mute yourself during the tutorial to guarantee a smooth session. Okay, let me hand over to Kishor. Okay, thank you.
Yeah. Yeah. Thanks, Zain. So let's today talk about topology, and today it's tutorial number 4, and we are going to talk about topology. In particular, we will focus on uh, Z2 topology, like Z homology and cohomology, and which will be basically Z2 homology and cohomology. So before we get there, let's try to see a few examples. Also, one thing I would like to mention that there is no background required, I would say, in topology to understand the concepts here. So no prior background is assumed. Okay. So let's first try to see some of the motivating examples. So like this is first example. So that this object, this is a cube, and in a cube, this is what we call vertex. And this is what we call an edge, and this is what we call a face. A vertex can be considered a zero-dimensional object. An edge can be considered a one-dimensional object. A face can be considered a two-dimensional object. Now let's count number of vertices. So number of vertices that we have here is basically 4 plus 4, 8 total. So there are 4 vertices in a cube. Number of edges, that is basically 4 plus 4 plus 4, so that's 12. And number of faces, that's basically 4 and then top and bottom, so that's 6. Now let's now do V minus E plus F. When you do that, you get 8 minus 12 plus 6, which is equal to 2. Now somebody can ask, why are we doing this calculation? And this is a very straightforward thing. I mean, even I would say a student who has just started like understanding cubes, they can do this calculation. But there is something interesting going on. Whatever we did here with a cube, you can do it with a tetrahedron. So there your V is 4, E is 6, F is 4. Now if you do V minus E plus F, so if you do V minus E plus F, you will get 2. Take cube or what we call hexahedron, whatever. You do this, you get 2. Octahedron, 2. Dodecahedron, 2. Icosahedron, 2. We are always getting this number 2. So something beautiful is happening here. And actually, every convex polyhedral object, it satisfies the relation. V minus E plus F equal to 2. So if you go to, high school or something, and if you want to, like give kids some puzzle, you can ask them to calculate V minus E plus F, and they will be amazed to see that it's always 2. I mean, for objects of certain kind, like, some polyhedral object, convex polyhedral object. So this number that we calculated, V minus E plus F, it has a lot of beauty. And this is what is called Euler characteristic. So this is like, your first, I would say, I mean, like for many people, this can be first entry point to topology. So this is called Euler characteristic. And actually, there is a characterization of Euler characteristic of general objects using something called alternating sum of Betti numbers. So you have B0 minus B1 plus B2 minus B3 plus B4 and so on. So it's alternating sum in the sense that they plus minus. You see that the sign keeps on changing. So it's an alternating sum. And this Bn here is called nth Betti number. I haven't defined what is a Betti number. I will later talk about what is a Betti number. So no need to worry if I'm just telling you that this number V minus E plus F for general object. I mean, you can calculate this Euler characteristic. Here we are talking about convex polyhedral object. For more general objects, you can talk about Euler characteristic, and you can calculate it using Betti numbers. And when people do topological data analysis, this Betti number is very important. So for example, many of you might have seen this paper if you're interested in quantum algorithms by Seth Lloyd, Silvano, and Paulo Gianardi, where they calculate Betti numbers. So you see that starting from something very simple as a cube, there is some connection which goes up to Betti number. And I think this you might find interesting. So this is first example, okay? Now let's take another example. So this is called bridge of Königsberg problem or something. Like I think you can find this on internet, on Wikipedia also. So you see that there are 7 bridges, 1, 2, 3, 4, 5, 6, 7. And there are 4 different, you can say cities. So there's some city and they are like islands or disconnected pieces. And they are connected by bridges. And someone asked, is it possible to find a path that would traverse each bridge exactly once? So you can come, then you can go like this, but you can come, and then you can go like this, and then you can come, and then you can go like this. But is it possible that without going through this bridge or whatever, I can traverse this bridge also one? So you can try to come up with, so this attempt that we did right now, it failed, right? It did not give us a correct, it did not work out. Because now I am stuck here. If I want to go to another island, I have to double cross one of the bridges. But maybe I lack imagination. Is it possible that I can do it? And for a long time, people were trying these, that possibilities, and until when Euler came and said, no, you cannot do it. So basically, you can take this problem and you can abstract it out as a graph problem, where these cities, there are like 4 of them, let's say, or islands, and every bridge is an edge. And then he proved that such a walk is possible if a maximum of 2 vertices of the graph is of odd degree. Odd degree means how many vertices are coming out of, how many edges are coming out of it. Now, if you look here, degree of this one is 3. Degree of this one is 3. Degree of this one is 3, and this one is 5. So all of them have odd degree. And how many vertices have odd degree here? 4. But Euler says such a walk is possible if maximum of 2 vertices of the graph is of odd degree. And here we have 4 vertices of odd degree. So obviously such a walk is not possible. So that's what Euler proved. So you see that again, we are not worried about, how the bridges are aligned, this, that, all the details. And this is the power of abstraction. Like sometimes you can get rid of some details that are not that useful. And at an abstract level, you can try to think of the problem, and you can get, general solutions. So that's what Euler did here. So that's second example. Third, many of you might have seen in memes like on Facebook, LinkedIn, whatever, Twitter, X, that, a coffee mug and a donut, they are basically same object. But in what sense they are same? Somebody can ask this question. So 3 examples we just looked at. First example was this Euler characteristic. Second was the bridge of Königsberg. And third one was basically this, copy-mug and donut. And you see that through these, basically, we get some hint of, topology. And this makes us feel, like maybe it's good to study topology. And obviously, this is like the starting point, like, I mean, you can use this to study many interesting things such as topological quantum codes and so on. But even to understand some basic things, there is some nice topologies going on. So topology is beautiful. So obviously we will not be into like going into details of things, and it's just one session and we can't cover everything. So we will be covering things at a level like which can help us understand, let's say, topological quantum codes in the future session, or make sense of Tori code that we discussed previously. So we won't be rigorous like as a mathematician, but it will work for us, I mean, because I mean, if we try to go into that detail, I mean, it will take a lot of time, so we can't do that. So let's try to understand some basic topology. So the first thing that we need to understand for basic topology is this thing called topological equivalence. And our notion of topological equivalence comes through something called homeomorphism. So this object, this thing, homeomorphism, will be important for us. So yeah, I had cut here. There is no need of continuous here because it's in the condition. So what is homeomorphism? So it's a function between two objects or topological spaces. I mean, there is a rigorous definition of what this thing is, but you can think of two objects, like let's say, I have a coffee mug and I have a donut, and a function between two objects that is continuous has a continuous inverse function. So it's continuous in the forward direction, continuous in the backward direction, and is a bijection, which means 1, 1 and on to, hence invertible. It's a forward, continuous coming backward. If such a function you have between two objects or topological spaces, then you call it homeomorphism. Okay. And examples are something like continuous stretching, bending, like, you can think of, like through bending, you can go and then come back, and there is, like it's bijective. So when we say two objects are topologically equivalent, like coffee mug is equivalent to a donut, we mean equivalent up to homeomorphism, which means there exists a function between the two objects, which is, continuous in the forward direction, continuous in the backward direction, and is a bijection. Okay. So I hope that makes things, like more rigorous than just saying that, the copy mug and donut are topological equivalent. So what it means that they are equivalent up to homeomorphism. So now we are talking about some operation, like, homeomorphism, like, some function which is uh, inverse, which is continuous in both direction and is bijective. But are there certain quantities, certain properties, like, that remain unchanged under homeomorphism? Like, one can ask a question, because that will help you tell which objects are, can be put together in same family. So the properties or numerical quantities that remain unchanged under homeomorphism, they are called topological invariants. So they are called topological invariant. So Euler characteristic that we just, like, I mean, we saw here, Euler characteristic, this is a topological invariant. Okay. So under homeomorphism, Euler characteristic does not change. And so you can calculate Euler characteristic of this object, Euler characteristic of this object, and we will see actually that Euler characteristic of these two objects is same. Hence, they are, like, I mean, they are same. Yeah, I mean, that's why they are same picture. Yeah. Okay. So we will see that. So the Euler characteristic can be generalized. So when we are talking about Euler characteristic, we're talking about vertices, edges, faces, but, I mean, But for general spaces, how can we do it? How can we get the notion of this Euler characteristic? And you can get that using something called cellulation. So cellulation basically means division of a surface into polygonal cells. So think about, like you have some kind of many people might have seen some soccer ball or something, right? Which has like this pentagon and hexagons, like, cellulating it. Or triangulation, like you can triangulate. Let's say, for example, here is a sphere and we are triangulating. So let's take torus. Torus has, number of faces L square, number of edges 2L square, and number of vertices L square. I mean, we saw in the previous case, right? I mean, there was this story code for which we were using squares, we cellulated it, and we calculated this quantity. When you calculate E minus, we were calculating, right? V minus E plus F. That was our Euler characteristic. So you calculate that object. V is how much? Number of vertices, L square. So that's L square. Number of faces, L square. So that's L square. And edges was 2L square. So put it here. So the Euler characteristic of torus is how much? 0. On the other hand, Euler characteristic of a sphere, you can triangulate it, and then you can count number of vertices, edges, and faces, and that is 2. So the Euler characteristic of a torus, torus and a sphere is not same. Here we have 0 and here we have 2. So these two objects, they are topologically inequivalent. We cannot go from one to another through homeomorphism. On the other hand, if you remember, we saw like our first example, motivating example, where for cube, the Euler characteristic was 2. So you see that Euler characteristic of cube is 2. Euler characteristic of sphere is 2, which means they are, they are related to each other by homeomorphism. So I can actually, you can imagine, right? I can take a cube and I can just do this and make it, like a sphere. So through this bending and stretching, I can go from here to here. But to go from here to here, I had to create holes, So that already tells you that, maybe I need to talk about holes, and how to capture that maybe will give us some insight. Okay. On the other hand, you can do it for coffee mug. For coffee mug, you can calculate the quantity. And you can do the cellulation and you can calculate for coffee mug and you will get again 0. So that will tell you that coffee mug and torus, they are equivalent, topologically equivalent. But torus and a sphere, they are not topologically equivalent. Or coffee mug and a sphere, they are not topologically equivalent. But a sphere and a cube, they are topologically equivalent. And so on. You can play this game. So the object that we need to care about, which helps us count number of handles in a surface, is this thing called genus. Like that's what people call it, genus. So for example, here, there is no handle. So it has genus 0. This has one hole, so it has genus 1. If a sphere has n handles, then it has genus n. So you can think of a coffee mug as a sphere with one handle. So it has genus 1. And torus also has genus 1. So in that sense, a donut and a coffee mug, they are homeomorphic to each other. Like they are topologically equivalent. So there was a very nice statement that has been proven, which says that the Euler characteristic, the object that we were interested in calculating, for any compact orientable surface. Okay, there's a bit of jargon here. So compact means, closed and bounded. That's what it means, more or less, yeah. And orientable, what it means, I mean, you don't need, even if you don't understand, it's fine. Maybe you can think that a sphere is orientable, Mobius strip is not orientable. And what orientability basically means that to every face, you assign an orientation, let's say clockwise or anti-clockwise or whatever. such that every adjacent cell, if they agree on that orientation, then you say that that surface, like is orientable. If that does not happen, then you call the surface is not orientable. So, for example, Mobius strip, many of might you have it goes and then something weird happened, right? I mean, like you can convince yourself it's a non-orientable surface. So for every compact orientable surface, of genus G, the Euler characteristic is 2 minus 2G. And Klein in 1882, which is like, I don't know, maybe 150 years almost ago, had shown that all compact surfaces with genus G, they are homeomorphic. So we know homeomorphic, we know genus, and we know, like sphere with G handles. So what they've shown that you just need to count, how many handles it has, and that will be okay. Like that will give you a lot of insights. So you see that for cube, there is no handle, there is no hole. So its genus is 0. Now you calculate this chi. So chi is 2 minus 2G, and if G is 0, that is 2 minus 0 equal to 2. So for cube, we get the number 2 back here. On the other hand, for torus, if G is equal to 1, so if you calculate 2 minus 2G, that is 2 minus 2, that is 0. So for torus, we are getting 0. For cube, we are getting 2. Like, recovery, what we had here. So Klein basically managed to give a more general statement, which tells us by counting genus, you can calculate, the Euler characteristic. Okay. So let's now apply it. So for Tori code, number of encoded qubit is 2 minus chi. Like, we will try to prove it. And then let's see, like whether it can be useful or not. So for Tori code, I mean, in general, it's because it's a stabilizer code, the number of qubits should be n minus m, where n is a number of physical qubit, m is number of like independent stabilizers. But n is equal to e, number of edges. I mean, that we already saw in the previous case. And m is basically v minus 1 plus f minus 1. So f minus 1 corresponding to placate stabilizers, and b minus 1 corresponding to vertex stabilizers. And you have to take the minus of this to calculate k, which is number of logical qubit. So that is nothing but k is equal to e minus v minus f plus 2. But then that is nothing but 2 minus v minus e plus f. And that is nothing but 2 minus chi. So number of encoded qubits is basically chi. So maybe we can change, and this chi is what? Chi is 2 minus 2G, right? Chi is 2 minus 2G. So you see that if we take a surface where chi is 2 minus 2G, k will be 2 minus 2 plus 2G, which is 2G. So somebody was asking earlier, Proletiha, that we are doing so much work and we are getting 1 qubit or 2 qubit. Maybe that is like, too little. But, it's because you have 1 hole. You increase holes, you will get more qubits. So if you have a surface with, let's say, G holes, then you will get genus G, then you will get 2G many qubits. And that's what people do when they try to do, like, hyperbolic codes and so on. I mean, they are basically, you try to, like encode it on a higher genus surface. And that can help you increase the number of logical qubits. So that's the idea. Like, we can take a G torus and the number of encoded qubits will be 2Z. So you see that this simple idea helps us without doing any complicated mathematics. We have seen that, like how, we can generalize Tori code to G Tori code, where instead of having 2 logical qubits, we can have 2Z logical qubits. So we discussed a few motivating examples, and we discussed some basic topology. Now we will discuss homology and then cohomology and then summarize it. Okay. Sorry, I'm going a bit slow to make sure that everybody is understand it. So today it might happen that we exceed the time and because we cannot spill it over to the next session. I mean we will try to cover it today. So it might take 15 minutes, maybe less, more than the regular sessions. I hope that's fine. I mean, yeah, yeah. So the goal is that I don't want to rush over things like yeah. Okay. So so let's say now let's try to understand homology. Again, we won't use any complicated mathematics, but you will see that this concept, they are like easy to parse and we will be able to use it for error correction. Make sense of that. So homology is basically a mathematical field which abstracts and generalizes the notion of something called boundary. So in the last session, you might have seen this thing, right? I mean, we were saying that let's say there is some error, there is some kind of a string, then we have to measure some operator which are at the boundary. And like that helps us figure out what error actually happened. I mean, even if you don't remember, it's okay. But I'm saying that what is a boundary? Like, I mean, it's a very nice idea. And homology basically tries to understand that. And then you can define something called co-boundary, which is a dual object, similar to bra is dual to ket. It's similar kind of a dual to define through inner product space. And that will help us come up with something called cohomology. So we will try to understand that. I mean, so let's just go through everything step by step. So our focus will be something very simple. We will focus on aspects of homology relevant to qubit topological codes. Okay. I mean, you can focus on qubit topological codes also, but it will become more complicated. But so we will start with something simple. So we start with homology on the group Z2. It is the simplest form of homology. I mean, for qubit, one can maybe look at ZD, but I think there is no need. I mean, maybe qubit is a good starting point, and you can always understand the simple thing and complicate it later. So we will look at homology on the group Z2, which has two elements, like 0 and 1. And we will look at square lattice cellulation. So that will make life further simple. Why? Because if you look at the square lattice, so in the Tori code that makes life easy, because for a square lattice, the dual lattice is also square. So it's self-dual. So once you understand, I mean, you don't need to do extra work. On the other hand, if you were doing, like, I mean, triangle, then it's not self-dual lattice, and then you have to place some. So I think, but basic ideas are already captured. So we try to make the thing just the simplest possible. That's what our focus is, and we will try to understand it here. And obviously, there's a lot of complications one can add here. So this is our focus. Okay. Now let's focus on, let's recall Tori code. Like, and even if you don't remember, I mean, you can just take it for a fact at the moment. If you remember, like you can see. So there we had a square lattice with periodic boundary condition. That's what we had. So we are working with square lattice. And this lattice can be thought of as cellulation of the torus. So we had torus, and on that torus, we basically we cellulated. I mean, there was a picture somewhere, right? I mean, you cellulate the torus using the squares. So you see that there are squares, and you are cellulating a torus. And we had three kinds of object. So we had vertex, which was 0-dimensional object. We had edge, which was 1-dimensional object. And we had placates, which was 2-dimensional object. So we had 0-dimensional, 1-dimensional, 2-dimensional, three kinds of object. Okay. And that's, we can go for a higher and dimensional Tori code and all that, but that's, like only can complicate things. Okay. So this is what we had focused on and tried to understand. So in homology, let's say we can define something called N cell. Okay. So an N cell is an n-dimensional object in a cellulation. So for example, if you triangulate, then, like you basically, you can, or let's say, so in our case, we were cellulating with a square, right? So we had 0 cell, which was vertex. We had one cell which was the edges corresponding to tori code, and two cell which was placket. So it's just a naming, like we were calling vertices. We can call vertices as 0 cell, edges as 1 cell, and plackets as 2 cell. And these are nothing but, I mean, any n cell is an n-dimensional object in a cellulation. Yeah, so that we will keep in mind. So once you understand a cell, like n cell, let's try to define something called chain, because many of you might have seen this thing called a chain complex and all that. Like, I mean, let's try to like understand this. Yeah. So what is a chain? So chain, I mean, in the case of Z2, is nothing but an assignment of elements of Z2 to every one-dimensional object on the lattice. So let's say I'm talking about one chain. So if I'm talking about n chain, I have to assign elements of Z2 to every n-dimensional object on the lattice. If I'm talking about one chain, I have to assign element of Z2 to every one-dimensional object on the lattice. Because it's one chain, that's why we are assigning to Z2 to every one-dimensional object. So this is one example. Like, this is a, like cellulation using squares. So this is your tori code lattice. And here you can assign 1 or 0. So let's say, so these are edges, and to edges you can assign 1 or 0. You can think of assignment of 1 means that edge we are including. 0 means it's being excluded. So you can think of it's more like a set, or the other ways. I mean, whatever way makes you think, like you can think of it. So it's just an assignment, like to different edges, we are assigning 1 or 0. I mean, I could have very well assigned this 0, this one 1, but that would have been another example of one chain. Okay. So I can take an example of one chain, I can take another example of one chain, and I can add them. And the addition will be how you do in Z2, like 0 plus 0 will be 0, 0 plus 1 will be 1, 1 plus 0 will be 1, and 1 plus 1 will be 0. Like this is how you do the addition. So for example, here you see that I have 1 here, I have 0 here. So 1 plus 0 is 1. Here I have 0, here I have 0. So 0 plus 0 is 0. But here I have 1 and here I have 1. So 1 plus 1 is 0. So it's very simple addition. To every one-dimensional object, I'm assigning 0 or 1 element of Z2. And when I'm adding, I'm following the rule of Z2 addition. So that's how I'm adding. So the set of one chains, they form a group. So you can edge-wise, you can do addition modulo 2, and that will be a valid one chain. To add 2 one chains, and it's a valid one chain. It also follows associativity, like I add one n chain with another one chain, and then I add with the third one chain. Like I could have very much, like, I mean, did something else also, like second and third and then first one. There's an identity operator, which is assignment of 0 to every edge. So it's an all 0 one chain. Okay, because when you add an all 0 one chain to any chain, you get back the same chain. So it's an identity operator. And there's an inverse also, because for every one chain, because you're working with Z2, it's self-inverse. So if you add the same object, because, like, I mean, in Z2, every element is self-inverse. Every chain, one chain is self-inverse. So it's a group. And actually it's an abelian group. So if there are E edges, then, like, I mean, that tells you that the number of such group elements is 2 to the power E. Okay, so that's one chain. So there was one example I told you, right? That you can think of it like if assignment 1, that means that edge is included, and 0 means that is excluded. Like you can think like that, for example. But the same thing same trick I can play with, like, I mean, 0-dimensional object and 2-dimensional object, right? Or n-dimensional object. Now in the tori code, like, in our tori code case, we have vertices, edges, and faces. So corresponding to the edges, we got, like, one chain. But corresponding to vertices, I can play the same trick. I can assign an element of Z2 to every vertex, and that will be 0 chain. I can assign 0 or 1 to every placate, and that will be 2 chain. In general, you can assign an element of Z2 to every n cell, let's say for the more general case, and that will give you something called n chain. So I hope that makes sense. Yeah. So we explained using 1 chain, but you can play the same game, for example, with, let's say this is an example of a 0 chain, and this is an example of something called 2 chain. Because here we are assigning element of Z2 to every 0-dimensional object. Here we are assigning element of Z2 to every 2-dimensional object. So that's why it's a 2 chain, and this is a 0 chain, and this is a 1 chain. In general, n chain assigning element of Z2 to every n cell. So let's say Cn is group of n chains, like that's what like the lowercase n means. And you say that C belongs to Cn means it's an example of a n chain. So for example, a small c belonging to C1 means it's a 1 chain. So if there is some C that belongs to C2, then you call it, it's a 2 chain. If some C belongs to the group C0, then it's a 0 chain. Means assignment of 0, 0, 1 to every 0-dimensional object, which is vertex, for example. Okay. So we understand, this group. So we have first group. We have come up with first group, which is group of chains. Like, and there can be, we can have like, we can have 3 kinds of group, for example, here. We can have C2, C1, C0, I mean, in our toric case, for example. Okay. So now let's look at this thing called boundary map. So boundary map, you can think of it as, it basically, it's a homomorphism, I mean, which takes you from n chain to n minus 1 chain. Now, obviously, like there is some math and jargon and all, but let's try to see it with an example, and then you will see like what I mean. So for example, here I have, like a 2 chain where I have assigned 1 here, and everywhere else, like, these are not counted. So these are being assigned 0. Now, what is the boundary of this placate? So boundary of this placate is basically this edge around it, right? I mean, so let's say this object here, its boundary is nothing but, like this, right? Like its boundary is this red object. So if you start with a 2 chain, its boundary will be a 1 chain, which is nothing but, like boundary chain corresponding to that 2 chain. So you can take, let's say, for example, some chain, which is, let's say, 2 chain, and you can break it down in terms of 2 chain generators, which can be, corresponding to every, whether a particular, phase is counted or not counted. So in that sense, because it's a group, right? So I can write it in terms of generators, and then I can add a coefficient. So that's how I can represent a general 2 chain. And a boundary map, a 2 boundary map, because it's a linear, it's like taking, like for every Cj, I can write its boundary and then combine with corresponding region. So another interesting example could be, like here, let's say this object here. So I count this, these 3, like faces. Now, what is its boundary? So its boundary is basically, this is the boundary, right? I mean, because this edge is here, right? And if you see, this is what we get along this line, all these are included. I mean, one can ask, why did we include here and not here? Because you can see there is a dashed line here. So basically, it means that periodic boundary condition. So this is included, which means we don't have to double count. So that's why instead of this, I just wrote it here. So you see that, you start with some 2 chain, apply boundary operator, boundary map, and it gives you a 1 chain, which is boundary of that 2 chain. So it's a map, let's say in this case, delta n will take you from Cn to Cn minus 1. So it will give you that n minus 1 chain which is a boundary of the n chain. So that's how you look at it. So for in this case, n is equal to 2, and when we act it on C2, we get a 1 chain, an element of C1. So I hope that makes sense. So let's say now you can do the same thing for 1 chain. Now when you apply 1 chain, 1 boundary map, it will map 1 chain to 0 chain, because delta n will take Cn to Cn minus 1. So when you take n equal to 1, you go from C1 to C0. So for example, this object here, what does it mean? It means that, like this particular edge we are talking about, what is its boundary? Its boundary is basically this. And that's what we get, like here, these two are included. I mean, similarly, you can calculate, what is the boundary of this object. So this object again is like you have a string here, and then you have a string here. What is its boundary? Its boundary is here, here, and then here, and then here. And you see that that's what we get. We get 1 here, and this one corresponding to this one corresponding to this one corresponding. I hope that makes sense. So in general, you are taking an n chain and you are mapping it to n minus 1 chain. Okay. So what is a boundary map for 0 cells? Now corresponding to 0 cells, one can say we start from C0 and we have to go to C minus 1, but there are no minus 1 dimensional objects. So in mathematics, like when you run with this kind of issue, you just come up with a, a definition, some rule to follow, so that we don't have weird things happening. So you can say that you can define a 0 boundary map, which when acts on any chain, it gives you, like a null chain. Like so 0 n is, let's say, null n chain, and when you act on any chain with, like delta 0, it gives you n minus 1 null chain. So null chain was our additive identity, if you remember, for group composition. Like you add it to any chain, you get back the same thing. Okay. So we understood, like this boundary map. Once we understood the boundary, the next thing is cycles. So you see that, like we are talking about some map delta n, which is taking us from Cn to Cn minus 1. But then one can ask, what can there be, like objects which does not have any boundary? And these objects are called cycles. A cycle is a chain with null boundary. So basically what it means that I can, when I act on delta n on C, that gives me 0 n minus 1. You can also think of it as all elements which are in the kernel of delta n. So all elements which are in the kernel of delta n, that gives you cycle. And based on that, you can again define a group called group of cycles. Okay. So cycles form a group. Like let's say delta n C is 0, delta n D is 0, then delta n C plus D is also 0. And you can check all the properties. So you can come up with a group called group of n cycles. So we have a map delta n, we have a group Cn, and we have a group Zn. So Cn is a group of chains, Zn is a group of cycles, and delta n is a map. And we will tie these things together. Final thing is coming. So finally, we are coming up with this thing called boundary chain. So boundary chain, you can think of as image of, like, so n boundary chain is image of n plus 1 boundary operator. So n boundary chain is any n chain which is boundary of n plus 1 chain. So you start with a chain, you act boundary operator. Obviously, if it's a cycle, then you get here 0. But in general, like, I mean, that may not be the case. And you can think of a boundary chain as image of the delta n operator. So if you look at it, I mean, let's look at like, so here it's written in delta n plus 1, but now let's write everything in terms of delta n, and we will see like things come out. So we had delta n, which takes us from Cn to Cn minus 1. So the domain of delta n, the domain is our group, like the group of chains. The image is basically the group, which is, like the boundary group, like we can call it. So because the group of the boundary chain is nothing but any n chain, which is the boundary of n plus 1 chain. Like that's how we are defining, right? So it's image of the boundary operator. And then we had also a kernel. So kernel, so here in this Bn minus 1, because we're working with delta n, and kernel was Zn. So we have three kinds of objects. We have the group of chains, we have group of boundaries, and we have group of cycles. Okay, we have three kinds of objects: group of chains, group of boundaries, group of cycles, and all of them are coming from, like your boundary operator. Maybe you can pause it a bit here. Okay. But something beautiful happens that every boundary is an n cycle, but not every n cycle is a boundary. For example, I can have a non-trivial cycles, and then it's boundary of, like no chain. Like I can loop around, for example, something like this or something like this. So we have these three objects, and we have chains, we have cycles, and we have boundaries. And every cycle is a chain, but not every chain is a cycle. So sorry. Every cycle is a chain, but not every chain is a cycle. And similarly, every cycle is a boundary, but not every boundary is a cycle. So there can be a strict separation between them. Okay, that's what we. Sorry, battery got discharged. So there are these three groups, and homology basically. Basically, this is where I wanted to come to. So in homology, we try to study the property and interplay of these groups. Like there are these three groups: group of cycles, group of chains, group of boundaries. Group of chain on the top, then group of cycles, and then group of boundaries. Okay, I hope you. Yeah. And all of them are related through. All of them are related through this boundary operator. Okay. Like basically Cn is domain, Bn minus 1 is image, and Zn is kernel. So by this, looking at the domain, image, and kernel of this operator, we are getting three groups, and the groups have this relation. Yeah. Also, it's nice to see that, because boundary of a boundary is a null chain. So when you look at a chain, you calculate its delta n, it gives you a boundary. But because that boundary does not have a boundary, you get a null chain. So this lemma, it is very useful. Actually, we will use it, when we study topological quantum codes. It's called fundamental lemma of homology, which says that boundary of boundary is a null chain. It's zero. So let's now look at, like the Cn, Zn, and Bn. Now, what I can do is that I can define some notion of equivalence. And my notion of equivalence comes through, like this boundary. So I had a boundary chain, right? So I will say that two chains C and D, they are equivalent if they are equivalent up to addition with a boundary. And this might remind you, like the stabilizer operator thing, like let's say, or logicals, like, there is the stabilizer and then there's something and you are multiplying and it's the same thing. Like, anyway, when we talk about topological quantum codes, we will revisit this again. But what is telling you that I can actually start with this group Zn, and I can quotient it with Bn, and I can define some group called Hn, which is what people call homology group. No. And it's basically this idea that, like you are saying that I can add element of boundaries group, and still if I remain in the same set, then they are equivalent. Anyway, I think I made a jump here, but I will explain this slowly. So 2n chains C and D, they are homologically equivalent. If they are equal up to composition with an n boundary B. So I have a chain C, I have a chain D, and if there exists a boundary B such that I can go from C to D, then I will say C and D are equivalent. Okay, very nice. So I can define, like this. So I had this group Zn, group of cycles, and Bn is the group of bonds, and I can define this quotient group, which is called nth homology group. So somebody can ask, what is a quotient group? So quotient group, I think for that you need to understand, things like cosets and so on. But even if you don't know quotient group, I can give you a small example to help you understand that. So let's look at like set of all integers. Set of all integers is like something like -15, -14. It's many things like 0, 1, 2, 15. But let's say I'm interested in whether an integer is divisible by 5 or not. So any integer which is divisible by 5, I can write that by 5z as 5z. Now, in this way, I can actually divide all integers in actually this. I can write in this format, like it's 5z plus 1, 5z plus 2, 5z plus 3, or 5z plus 4. Now, any two integer which differ by 5, they will belong in the same quotient group. Sorry, they will be equivalent. They will be in the same equivalence class, basically, right? So for example, here Z5. So here it's Z5. Yeah, I give some example. Maybe this is not the right one, but yeah, you can always talk about this quotient group, which captures the idea of equivalence. Like you are trying to take a set, and you are breaking it into smaller. So for example, here in this set I have 5z. In this set I have 5z plus 1, 5z plus 2, 5z plus 3, and 5z plus 4. And any element which is here and here, they are related to each other by a multiple of 5. Any element which is here, they are related to multiple of 5. So similarly, I would say, you can take any two cycles which are related by the same, like, some boundary. I can put them in the same equivalence class, and I can define this nth homology group, which is Zn quotient with Bn. Okay. And my nth Betti number is nothing but rank of this nth homology group. So that's what the Betti number is, like, that we were talking in the beginning, which is nothing but rank of Zn minus rank of Bn. So you count the, like this, the rank of the boundary group. You count the rank of, cycle group, and then that will give you the Betti number. Okay. So I hope that, makes sense. So for example, for torus, one can calculate beta 0, beta 1, beta 2, and verify that it's indeed equal to 0. Yeah. And there is some more thing that you can do. I will not go in detail, but slides you can see later. Yeah. Also, there is a nice relation between Cn, Zn, and Bn minus 1, coming from the fact that delta n takes you from Cn to Cn minus 1, and Cn is nothing but domain, Zn is nothing but kernel, and Bn minus 1 is nothing but range. And because rank of domain is nothing but rank of kernel plus rank of range, like that gives you this relation. And using this relation, actually, you can prove that, that chi is equal to beta 2 minus beta 1 plus beta 0. In general, you can generalize it to, like alternating some of Betti numbers, but because, like this beta is nothing but beta n is nothing but rank of Zn minus rank of Bn. So you can just use this relation here, like this thing. And then the fact that beta n is a rank of Zn minus rank of Bn, you can prove this. So maybe this you can take a small homework or something. Yeah, that chi is beta 2 minus beta 1 plus beta 3. And in general, chi is nothing but alternating sum of Betti numbers. Okay. So I hope, I try to keep it as less technical as possible, but all the concepts which are needed for to understand topological quantum codes are here. And from the homology side, and maybe, this gave you some feeling. Now we will, we will look at cohomology. So bear with me for some time, and I believe it will be useful. Yeah. So we looked at homology. So in homology, we looked at chains, boundaries, and cycles. In cohomology, we just put a co in front of it. Now we will look at co-chains, co-boundaries, and co-cycles. It's like they are like dual objects. The co-chains and chains, they are dual objects. So it's similar to, okay, let me write here. Yeah. It's similar to the dual thing that we talk about, ket, for example. So you have ket, the dual object is bra. Similarly, for chain, you get co-chain. So for example, what are the set of bras? So it's nothing but you have some ket, and the bra basically takes you from a ket to a complex number, right? If you have some ket, you activate a bra, you get a complex number. In Z2 homology or cohomology, a co-chain is nothing but you have some chain, and a co-chain, the inner product will take you to Z2, because we are working with, over Z2. It's same kind of object. So you can say the set of n co-chain is set of linear function which map each n chain to the group element Z2. And it's similar to bras, bare cheese. So if you understand ket bra dynamics, I think you can make sense of, chains and co-chains. Okay. So through this inner product thing, we will try to make sense of. Obviously, here inner product is any complex number. Take two quantum state, their inner product is a complex number. Here the inner product will be either 0 or 1 because it's in Z2. So let's try to see, like this thing called zero co-chain. So we have a zero chain. Actually, if you remember, we had talked about this notion of, dual lattice. So we had vertices, edges, and faces. And in the dual lattice, basically my vertex became face, edge remained edge, and face became vertex. Like, if you remember from the yeah. So in the dual lattice, there is this kind of, mapping that happens. So similarly, you have a chain, let's say zero chain, which is assignment of 0, 1 to every zero-dimensional object, which is vertex. A zero co-chain will be assignment of 0, 1 to every zero-dimensional, object. In this case, which is faces. And their inner product counts how many vertices which are in the overlap. So the number of vertices which is inside the dual placket modulo 2. So zero chain. So for example, here we have like, this is a zero chain. This is a zero co-chain. The inner product will be 1 because there is just one vertex which is in the overlap. So you can always take a zero chain and zero co-chain, and in this manner you can calculate the inner product. So zero chains are subset of vertices or equivalently an assignment of 0, 1 to every vertex. I mean, from our understanding of homology, zero co-chain is subset of plackets because, like in this relation that we just talked, in the dual lattice or equivalently an assignment of 0 or 1 to every placket in the dual lattice. I can similarly talk about one co-chain. But for one co-chain, you can talk about edges because, like in the dual lattice, edges get mapped to edges. So I have one chain, I have one co-chain. In this case, we will count how many times they have overlap, which means how many places how many times they intersect. And then you have to just add that modulo 2. So they intersect at 2 places. So 2 modulo 2 is 0. So their inner product is 0. So in this way, you can calculate the inner product. This inner product will be very important because this will help us calculate which operators commute or not commute in surface code, topological codes, and so on. So this inner product will be important. Will help us take care of the commutation relation. So one chains are subset of edges or equivalently an assignment of 0, 1 to every edge. One co-chain is subset of edges in the dual lattice or equivalently an assignment of 0 or 1 to every edge in the dual lattice. So that's how we talk about one chain and one co-chain. Okay, so like just a minute, I need to maybe switch off the turn off my Discord because I think I'm getting some depolarizing noise from there. Okay, so basically now let's look at cohomology. Yeah. So for two co-chains, so we talked about zero co-chains, we talked about one co-chains, and the two co-chains. I mean, it's similar kind of thing. Like we had two chains which is subset of plackets or equivalently an assignment of 0, 1 to every placket. Now, as we said here, in this case, now we have to talk about vertices. So two co-chains will be subset of vertices in the dual lattice. So here I talk about placket, here I talk about vertex to see this relation. So if you understand Z2 homology, Z2 cohomology is nothing but homology on the dual lattice. Because it's self-dual, life is easy. So basically, we have this inner product we can define similar to the zero co-chain case, and you can calculate the overlaps and so on, and we will see this in action in the next session. Yeah. So we talked about this thing called a boundary. You can define something called co-boundary. So let's say you have some chain C, and then you have delta n plus 1 some boundary map. So it will take you to some n chain, and you can take its inner product with some n co-chain. Actually, it acts same as the when you do the dagger operation. So it's like so it's like again the dual object of n plus 1 boundary map. So from the n plus 1 map get to delta n tilde. Yeah. So let's look at it's a group homomorphism on the co-chain, similar to the case where we had a boundary map, which takes us from. So basically a co-boundary map will give you a boundary of or you can call co-boundary of a co-chain. Like you have to just co everything. So we have here some chain, and so here we have a chain, and here we have some co-chain. And you can calculate, let's say, boundary of delta 1c. So that will give you 2 dots. And that is 1. But you can follow this relation, and you can instead of that, you can calculate boundary of this thing. So that is here. And now, because both of them are like one chains and one co-chains, you have to count how many places they intersect, which is one. And you see that you get the same number one in both cases. So you can use this, this relation that we have between boundary and co-boundary. So once you define boundary map, the co-boundary map is defined using this relation. And you can play and see the same thing again, like another example here. So for co-boundary group, cohomology groups, I mean, so for homology, we had in the homology case, we had three groups. Like, we had the map, boundary map, and then we had the group of cycles, and then we have the group of boundaries, and we had the group of chains. So, so we had actually Cn, and we had Zn, and they had Bn. And we had analogous object here also. And you can quotient it again, and you can get, like this nth cohomology group. And the rank of the nth cohomology group will give you in this alternate, this dual kind of Betti numbers, beta n. So once you understand homology, cohomology is just like dual characterization, at least in the case that we are thinking of. So for Z2, cohomology is simply homology on the dual lattice, but this does not hold generally. But who cares? I mean, for our case, it might, like, I mean, maybe it's okay. Yeah, I mean, but yeah, obviously, I mean, J for QDITs and so on, things will be more complicated. So thanks for, like bearing with me, yeah, like another 10 or something. So in summary, today we started talking with, like the Euler characteristic. We talked about the notion of homeomorphism. We said that, like what does it mean to say that, like coffee mug and the donut are like topological equivalent and so on. And then we talked about, this notion of n cells, and then the corresponding, like chains like 0 chain, 2 chain, n chain, and so on, like, and we talked about these different groups like Cn, Zn, Bn, and how do we go from one to another using this map, boundary map, and this inclusion relation, which helps us give, like this quotient group, and from there we get this Betti number. And the same thing we can do for, like the cohomology case, and we get the nth cohomology group. Like here you have homology group, here nth cohomology group. And we had also this fundamental lemma of homology, which says boundary of boundary is actually a null chain. And this boundary and co-boundary maps, they are related by this, like adjoint relation. So I think that's it. I think that concludes today's session, and I thank people who could, like bear with me today. And in next session, we will talk about it, yeah, in the more detail.
Okay, thank you, Kishor. Thank you, everyone. See you guys next week.